didn't know that there was anybody.
I know that dog. He comes from the house. He ain't yourn.
No, he's Mr. De Winter's.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by George Konidaris, who is a co-founder and CTO of Realtime Robotics. Thanks for joining today.
Thank you, Scott. Thank you for having me. It's wonderful to be here.
So you are the John E. Savage Assistant Professor of Computer Science and the Director of the Intelligent Robot Lab at Brown. And looking at your research, it looks like you're looking to focus on building intelligent, autonomous, general-purpose robots that are capable of really doing a lot of kind of wide variety of tasks and within kind of, undefined environments in a way. Can you elaborate a little bit more?
Sure, yeah. So the first thing I should say is that I think that, people talk about AI and general AI, and I think that humans are robots, not computers. And so I study AGI by thinking about how we might build generally intelligent robots. Right? And so one of the challenges that I focus on in my academic life, which is kind of very blue sky and kind of nerdy and not very application focused at all, in contrast to my work at Realtime, is how we can get a single robot to be able to do almost anything. And so there's this kind of gap between the way that the robot sees the world, which is through pixels and motors, which is this very low level interaction with the world, which we often call swampy, right? You're sort of doomed to interact with the world that way. If you're a robot, you have no other choice. But that's not how you want to think about problems. If you're playing chess, you don't want to think about the pixels that make up the view of the chessboard. Instead, you want to have an abstract conception of what a chessboard is and what the current chess position is. And you don't want to think about how you move your motors. You want to think about making legal chess moves. And there's a kind of leap in representation that humans are able to make when they think about things that way. Or it's really no problem to shift your view of a chessboard as a human. It doesn't change how you view it at all, or to change the exact characteristics of a chess piece. It doesn't affect how you play chess at all. And so there's this, humans are able to kind of reframe things from pixels and motors, and instead to be able to think about them symbolically and abstractly, which is the way that we normally think about things in AI. And my research in my lab is focused around bridging that gap, having robots that are able to frame problems for themselves in this nice kind of way that expresses the complexity of the problem and discards the complexity of the robot. Does that make sense?
It does. I mean, I think, oftentimes we will get into a car, drive for 45 minutes or so, and somehow arrive, and we kind of wonder, how do we get here?
Yes.
So clearly, we didn't get into the mechanics of the steering and the braking and the gas, but understood that abstract from a symbolism that we knew that we were on a certain path to travel. So really, some of the kind of the functional aspects took a second seat. Is kind of what you're referring to.
Yeah,
now,
that's exactly right.
On the level of AGI, again, because this is an area that you specialize in, many, including your peers, would say that this is nearly impossible to achieve, and putting a date would be kind of silly. What are your thoughts? I mean, should we even be thinking along AGI, or is that just more kind of hopeful thinking?
Oh, we should totally be thinking about it, right? It's the most important scientific question. It might be the most important scientific question that's open right now, right? It's certainly the one that has the potentially biggest impact to human life, and it's definitely doable. Like I don't believe that it's impossible. I do think it's like fundamentally deeply hard, and so I think when we talk about dates, we're talking in the order of centuries, not years. But that doesn't mean we shouldn't be chasing it. That doesn't mean it isn't fascinating, and it doesn't mean it isn't important. But it is properly studied, I think, mostly at universities and places that can take a much longer range view and take intellectual risks and be able to bet your entire lifetime's intellectual career on kind of asking questions about that may not pan out, right? That's sort of what universities are for. So it's really that order of a question. It's not a question of that it's going to be useful tomorrow and suddenly it's really on the like, okay, over the next century or two, how are we going to understand this kind of deep intellectual question?
I love that. I love that. And I was actually speaking with one of the leaders within the Oxford Institute around some of these aspects, including the ethics. So he definitely looks at it from that perspective as well. It's not so much about the feasible application right now, as much as thinking through the implications of that and how do we start to, from a design and other aspects, really think hard about that. Well, let's get into more of the practical aspects of this interview, because you're clearly a co-founder and CTO of Realtime Robotics.
Mm-hmm.
So just without getting into too much of the kind of genesis of it, clearly there's kind of an obvious need, right? I mean, with not just cage robots, shifting to more kind of free form things, moving freely around the warehouse, or maybe even airport, drone preparation, delivery, whatever it is. We're starting to get into this notion of many robots or swarmergy, and of course, it's not just there's something in front of me, so I stop, but it's a kind of an orchestration that is decentralized in a way. So, talk about robot collision avoidance and risk-aware driving, outside of a typical cage format.
So I think the thing that one has to always remember about robotics, and this is just like an iron law as far as I'm concerned, is that the more structured things happen and become practical earlier than the less structured things. Like that's why robots in warehouses running along tracks in a big grid happened without any arms happened before robots with arms in warehouses, and robots with arms in warehouses is still pretty structured. That's going to happen long before there's a robot in your kitchen, and that's because it's much easier to solve problems in very structured domains, because we can kind of do a lot of what a human would do, a lot of the thinking that a human would do, we can kind of do for the robot, right? So for example, I love to use this analogy because it hits home, especially with American audiences. One of the things that you do many, many times a day is you just kind of walk up to your fridge and you open it and you reach in and you grab something like a beer. And you do that often without thinking about, without having to know in advance everything that's in your fridge. And if I put you in front of a new fridge at a friend's house, you just kind of know what to do. You just generate that motion on the fly. Your brain does it for you, because brains are amazing. But actually, if you've ever tried to teleoperate a robot to do something like that, and it's an experience that I encourage everyone to do, it suddenly dawns on you that the vast majority of parts between where your hand starts and where the can of beer that you're aiming for would result in a collision with the world. There's all those drawers, there's all those other objects, there's your own body, there's all this stuff. It's actually really hard to solve that computational problem. And so what's happened in robotics up till now is we've just avoided that computational problem. It's too hard. So we will do things like we will build these giant factories that are so structured that you can completely predict where everything is down to the millimeter. Right? Automotive manufacturing factories, they will bring the car chassis to the exact same place. And then these robots will kind of repeat these motions blind, because that's kind of what they can do. That's sort of where the technology is at. And if you have multiple robots, a person has to choreograph those robots by figuring out the timing and the movements sort of in advance, so that they never hit each other. And this is like choreographing a ballet where all the dancers are blind, right? That's how hard that is. It's an extremely difficult task. And that's dumb. We shouldn't have to do that. And we have to do that today because robots are dumb. But one of the things that real-time has done is it's kind of solved this motion planning problem. It said, okay, that robot on the fly can take care of that for you. It will generate the motion. You tell us where you want the end effector to be, and we will produce the motion in a collision-free way. And we'll do that if there's 6 or 8 or 12 robots in the work cell. You all plug into our controller, and we'll just take care of that for you. You never have to think about it. They never hit each other. Everything just works. And so what that's enabling is it's enabling us to get to those less structured applications, to be able to break out of this extremely expensive, wildly over-engineered factory, to be able to do more stuff.
Yeah, this is this area is really exciting because when you talk about spatial perception and of course robots being able to work in an unstructured environment, it has huge economic implications, financial implications, because like you said, legacy factories are very much structured, very much defined. But as we get into transition from combustion engines to electric vehicle or electric vehicle plus hybrid that can handle, let's say, hydrogen, for instance, the factory floors are going to have to change. Moreover, at a kind of a bigger perspective is that at some point we're going to get into on-demand, almost 3D printed types of localized, special, custom-made piece components and systems, which means that both from a real estate, but also the inside of that factory floor is going to have to be constantly changing and dynamic. So this notion of fixed floor isn't going to exist anymore. So this becomes really important. And of course, the ability to switch on a dime, I think, is really important. So in the worst case, let me actually go back historically to like the World War I and World War II, having to switch, let's say, a car manufacturing company to start building tanks or ships and so forth, that's very difficult to do, right? So maybe you could talk a little bit about more practical uses of how this is being done with some of your customers. You may also like our quarterly Astor Perkins event that brings some of the most notable experts and category-leading startups in their area of sustainability and human survival on Earth and in space. To register, visit astorperkins.com/events.
Sure, yeah. So let me give you a specific killer app that turns out to be one of the things that our customers want kind of right now, large automotive customers. They have one of the common tasks that they have is they will bring a car chassis to a particular point, and they'll do that down to the millimeter, and then it'll be like kind of raised above the robot's head, and they want to kind of insert bolts, right? And because it takes a long time to get the car there, they want there to be like 6 robots in the same space, all putting in the bolts in parallel. And that is an extremely structured task on the one hand, because you're bringing the bolts to you're bringing the chassis to the exact same place. The bolts are always in the same spot. And the robots are making, roughly speaking, the same movements all the time. But of course, there's some process variation. So sometimes it takes a little longer and they get out of sync. And it takes something like 13 weeks to do just the programming to coordinate those 6 robots. Now bear in mind that the person building the work cell knows exactly where the bolts have to go, right? There's no mystery about that. And they have a perfect CAD model of the work cell and they know exactly where to put the robots. But even then, just making sure that these things don't smack into each other takes 13 weeks. And that limits how frequently you can do this update. And with the stuff that we're building, it takes on the order of a week. And that's because what we've done is we've sort of raised the level of abstraction about what the work cell engineer has to think about. They don't have to think about where all the robots on elbows go at a particular time. Instead, they can just say, allocate these particular bolts to those particular robots, these ones to these robots, go. And it all just kind of is computed on the fly. And so at the moment, what we're doing for large automotive companies is we're drastically reducing the amount of time it takes to get that same work cell function. But that's really just the beginning, right? Like that's the sort of obvious first thing. And then what's going to happen after that is it's going to be kind of robust. So if one of the robots breaks, you don't have to shut everything down. You just redistribute the tasks to the other robots. And then if you change that chassis, then all you need to do is just point out the new places you need the bolts to go, and you click go. And all that happens kind of automatically. And then if you decide you want to have 12 robots, which we're very shortly going to be able to do, then you get all that extra savings in speed. It just is a sort of turnkey thing, right? You no longer have to think about these stupid things. It's like writing a program on a computer and having to worry about the memory usage of all the other apps on the computer. Of course, you'd never have to do that. That's too complicated. It's the operating system's job to take care of that. In the same way, we think it's our job to take care of the robot motion. You tell us, where do you want the business end of that robot to go? And we just take care of all the other coordination stuff for you.
Now, some of the things that you're referencing, of course, is the product rapid plan that allows for quick creation of motion plans for single or multiple robots, so they can scale up or down quickly. Mm-hmm. And you mentioned some of the digital workflow creation, optimizing the icon optimize, as well as the programming. But I think the thing that caught my attention was really some of the core kind of IP that's been developed is this notion of accelerated motion planning using your proprietary algorithms that operates at some 1,000 times faster than conventional approaches. Yes. Can you talk a little bit more about that?
Sure, yeah. So and here I want to rewind a little bit to the founding of the company. So motion planning, this problem that we've been talking about, has actually been studied in academia for a long time. Right? So the first paper, the kind of problem was first formalized by a researcher at MIT that I did my postdoc with, Tomás Lozano Perez, and he did that in 1979, which was the year that I was born. Right? So it was a long time. And software solutions were just not fast enough, right? They were just on the order of tenths of a second or a second in many cases to do one plan, which is not ever going to get you anywhere. And so when I was a professor at Duke, before I moved to Brown, I had a very fortunate lunch with a computer architect, Dan Soren, and it was kind of at the beginning of, AI was getting trendy, which is nice to see. But it was also people were becoming interested in building specialized hardware. It was interesting enough, and it's clear that applications were important enough that maybe you didn't want to run this on a CPU or even a GPU. Maybe you would be interested enough to build specialized hardware. So we decided that was how we were going to think about attacking the motion planning problem. And so we were able to build the specialized processor that just knocked like 3 zeros off the time that it was required to do that in software. And that happens because the computational expense of what's happening in a motion planner is actually very distributable. So you can get the most parallelism out of it by building circuitry, because circuitry is naturally parallel because physics does that for you. And so that was the sort of core breakthrough, and that happened at the universities. That was a genuine sort of research breakthrough. And then we thought, okay, now we can do this. How does robotics change? And we sort of built the company around that piece of technology to start with, but then also kind of understanding what the industry needed and how we could help facilitate that change.
It's fascinating, absolutely fascinating. And thank you so much for that quick recap of things. Can you talk a little bit about not only a current product roadmap, but where can some of this kind of, both from the research side, but also the application side advance as we look into the future?
Yeah. So at the moment, what we're doing is we're building this kind of set of technology. We actually have a box called the real-time controller, and you plug your robots into that box, and it takes care of lots of stuff for you. And how you program the work cell is you talk to that box instead of the robot. So we really are becoming an interface layer. Mm-hmm. But the way that I see our fundamental value add is that we're sort of like half operating system and half development environment. So we're like an operating system in that we can take care of a lot of the boring bookkeeping that you need just to get your job done. When you automate a work cell, instead of worrying about where the robot's elbows are, you just think about where the business end of the robot is. Instead of worrying about like how you control this particular brand of robot, we have a driver for that. You just plug it in and it works. Same way that you just plug in a printer driver and you no longer care what brand it is. It just works in a sort of unified interface. On the other hand, we recognize that integrators, who are the people who build these work cells in factories, are developers. They're like programmers. And so, what we're trying to do, what we see happening over the next 5 years is we're going to kind of build out a suite of application development tools for them to be able to cater to their every need. Like, what do we do to make these guys more productive? How do we make their lives easier? How do we make them able to automate more flexible things, to be able to expand the set of things that can be automated, that are economically feasible to automate and technically feasible to automate? And just address those needs one at a time and push that envelope. So to give you an example of a couple of tools that I think will be very exciting coming up next. So we're building plugins for all of the kind of industrial process simulation tools, which are often used to build models of these work cells. So you can kind of use our technology inside these while you're designing the work cell, and it's all kind of seamless. And then you can kind of hit export, and it exports the model to our controller, and everything just works in one nice little loop. Another thing that we have that's coming out that I'm very excited about is an optimizer. So because we can do motion planning very quickly, you can load this kind of a model of your work cell in, and you can say optimize, and tell us what tasks you want to do with the robot, and we will conduct a huge computation, and we will optimize the placement of the robots and the allocation of tasks to the robots and the home position of all the robots to maximize your throughput. And we already have really good preliminary results on that. Like we can improve throughput by double digits on a computation that takes less than an afternoon. And so the way that we think about all these things, though, is that they support this development process. They're what make it easier to be for integrators to be more productive and deliver more powerful automated solutions.
I'm really excited about these two additional programs that you guys are developing and releasing. And certainly, I mean, immediately you could see the time compression in terms of time savings, as well as just this notion of optimization that otherwise would have taken who knows how many iterations to perfect. Incredibly valuable. I wonder at some point, as you continue to add additional capabilities, essentially, let's say apps, do you also foresee that you would want to open up your OS to other developers to add additional sets of capabilities? Don't forget to visit astorperkins.com to register for our next quarterly events. Past and current speakers include Damian Vaughn, former NFL player, Neil Gregory, Chief Thought Leadership Officer at the IFC World Bank, and many more. To register, visit astorperkins.com and click on Events.
Yeah, I think that that's right. So I think we'll get to the point where, we've taken care of a lot of the infrastructure for controlling the robots and making them go, and we've made programming them relatively easy. But it will be the case that there'll be a lot of value add to bring in we call these sort of plugins, right? So where people we have actually architected into our real-time controller a guest processor where you can say, okay, I want to be able to download my plugins maybe from these vision companies and plug in their cameras, or I would like to be able to say this particular company has built a really good grasp detector using a deep neural net, and it's the best thing out there, and I want to use that in my application. And then you'll just be able to kind of download these and try them out in a development environment way, just in the same way that when you're using like Microsoft Visual C++, you can download an API and you can say, I want to use this database API, and it plugs in and you run it, and all that stuff will be kind of layered on top. The challenge for us is that because we're running the operating system of the machine and we have like hard real-time constraints, we need a lot of control over what happens on that appliance. So that's why we ended up building an almost walled-off guest processor that is able to handle that without interfering with the kind of real-time control we need to be able to do in the arms.
I know so far we've been talking in the context of, let's say automotive company, or maybe it's an airplane engine company, let's say, and it's in the context of their organization. But once we start to take it beyond that, so let's say, for example, FAA, or those that are trying to orchestrate or organize and coordinate airplanes or drones, for instance, or in the case of emergency services, let's say that there's been a flood, hurricane, wildfire, and you need to coordinate fire, ambulance, and so forth, other services. But then as we get into kind of the future where things become more automated and you have not only human-driven vehicles, but let's say autonomous vehicles, autonomous emergency services, how can something like this be used to help orchestrate in, let's say, a city context, or in a flight context, or even a maritime? So right now, there's a ton of issues happening around the port because of lack of throughput, lack of resources and people, frankly. So you got a lot of cargo ships that's just waiting, docked in the Pacific Ocean. They can't get through the port because things are not moving fast enough.
Mm-hmm. Yeah, that's exactly right. So the one way to think about this is there's sort of two types of planning, right? One type of planning feels more like scheduling. You're going to say this guy's going to show up at 2 p.m. and they're going to get through, and that's kind of logical and discrete. And that's not really the kind of planning that we do. So there's a lot of advances that can be made in that sort of automated scheduling that don't really fit into our technology. But then when you find out that you've made such a schedule and you're actually trying to like move the ship through the port, then there's a motion planning problem where you actually think about the geometry of how things move through space and time. And you especially want to do that if there's multiple of these things moving through space and time at the same time, right? You kind of want those. It would be really great if those ships, instead of observing huge distances between themselves to make sure that they're safe, instead, if they could kind of all connect up to each other wirelessly, run a little motion planner, maybe attached to the port, and all move through it like maximum throughput while carefully avoiding each other, right? So that sort of problem we could imagine automating with this technology, and I think that would be very valuable. The other thing with autonomous cars is there's the coordination problem with autonomous car, but there's also the ability of the autonomous car itself to plan, right? So another way to think about this is we're pushing a lot of the basic physical intelligence onto the sort of distributed device, right? You're not trying to do stuff on the cloud, or you're not trying to pre-do stuff in advance involving a human. The device on its own can do quite complex planning, and that's really going to be necessary for autonomous cars when they're traveling at moderate speeds in very dense environments. Like if you've ever tried to drive in downtown Boston, it's not like a highway in California where the weather is beautiful and you can see everywhere and there's a nice big wide lane. There's people and bicycles and pets and everything everywhere, and actually you need to be very reactive and plan very, very quickly. And the details of your motion matter. And so I think this technology would really, really work there as well.
That's very interesting. Well, our last question for you is lessons learned in terms of any projects or product failures and lessons learned that you can share with others.
Sure. So I mean, I guess I have like a somewhat unique perspective because I am an academic, and so the rewards and the optimizations in academia are quite different to capitalism, let's say, right? And so one of the things that me and Dan, who are the sort of academic co-founders of this company, have always taken great care to do is to sort of understand the limits of what it means to be a successful academic and what it means in terms of vision and how far in the future you need to be and how you win at this particular game versus what it actually means to run a functional business. We've always been very hard-nosed about, no, we're gonna make real robots that work for real customers, and we're gonna be very focused on their demands and what they need. And that's been an incredibly enlightening process for me to see how deep deeply you have to engage with customers and the market and the industry to really deeply understand what it is they need, not just what you think they need, not what your vision of what robotics is going to look like tomorrow if they would all just listen to you, but instead to sort of meet them where they are and understand how you can make their lives better. And also at the same time to be able to see a path from making their lives better a little bit at a time to getting them, to make this big jump. And one of the challenges we see in robotics is in sort of heavy industry and things like automotive, because of the lack of this basic technology like motion planning, it's been inside this box for so long. Like, this is the box of things you can do. It's been inside for so long that they can't even see the box. They're not even aware that it's there, right? And so as an academic, you just want to go, there's no box. We should all go wild and everything will be great and life will be better. And that's just not how that is going to work. You have to slowly tempt them out of the box with things they can use and things that they want, and understand that, that your academic vision, your big picture doesn't actually align with reality necessarily. And you need to make those two things merge. And so that's been the core journey for me, which I found fun and interesting.
Well, I find that insight and your wisdom is so valuable because so many of our founders and, of course, the listeners and the constituents of this podcast are very much technical, and many of them are PhD postdocs and either current or former professors. So this is a very practical and relevant insight and advice. So thank you for that. I have been joined by George Konidaris, who is the CTO of Realtime Robotics. Thank you for joining today.
Thank you, Scott. Great to see you.
All right. If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.